quantum computing algorithms and machine learning. So I'll just give you briefly the today's coverage. Recap I haven't prepared because I thought of talking in my very first talk today morning. I'll be kind of wasting your time for 2 hours. Okay, so there we will kind of look into what has been done so far and try to recollect some of the concepts. Then the 11:45 session will be handled by Karthi Ganesh Durai, quantum classifiers, so purely on application of quantum computing in ML. And late in the afternoon will be a non-technical session on social connectedness and inspiration by Kumar Simha from Art of Living. So today's sessions are equally poised between technical and non-technical kind of stuff. Okay, so I hope you'll enjoy the sessions. Over to you, Shavani.
Thank you, sir. Good morning, everyone. So today there will be talk on introduction to quantum machine learning. So it will be given by our pillar of this FDP and Dr. Sathish Babu, sir. He just to introduce about him to the audience, he received his bachelor's and master's degree in computer science and engineering from Bangalore University, and obtained his PhD in Protocol Engineering Technology Unit Department of ECE at IISc Bangalore in year 2009. His research interests include information security, cognitive computing, applications for network controls, software computing solutions for cloud computing, scheduling and virtualization, data science, and many more, including quantum computing and others. He has published over 80 international journal conference papers with many publications featured in Scopus quartile journals and Web of Science journals. To mention the few, elsewhere, Computer Communication, John Willick, Journal of Security and Communication Networks, Journal of Intelligence System, many more. And he also has co-authored a book on mobile and wireless network security published by Tata McGraw-Hill, and a book on communication protocol engineering published by PHI India. So these books are widely used as reference in 15 Indian universities, and he also co-authored 8 chapters in edited book published by CRC Press and IGI Global International. So sir, his PhD thesis was dynamic security and authentication systems for mobile transaction, a cognitive agents-based approach, was selected as best thesis for 2009 by Board of Information Technology Education and Standards, Karnataka. He has worked as a co-investigator in joint research projects with IISc, Imperial College London, and Florida International University, USA. He has successfully investigated 3 projects sponsored by ABB India Limited, VTU in developing key management infrastructure, creating side channel attacks infrastructure, trust-based security solutions for ubiquitous networks. Sir serves as a member of board of BOE, BOS, VTU nominee, advisory board member for autonomous institutes in Karnataka and outside. He has served as a technical committee and program committee member in many international conferences. He is also a member of editorial board and reviewer of many international journals and conferences. He has conducted several proficiency courses at Indian Institute of Science on protocol engineering subject. He is a regular speaker in several international conferences and workshops organized by IISc Bangalore and many reputed engineering institutes within and outside Karnataka. Sir has successfully guided 4 scholars for award of PhD degree from VTU Belgavi. We are really happy to have you, sir. Over to you.
Thank you. Yeah, let me share my presentation. Okay, just a second. Is the screen visible? Good morning.
Yes, sir.
Okay. So, very good morning to one and all present here. I have kept my video off for various purpose. Okay, because you are seeing me on a daily basis. Let us not give you a problem of seeing my face for 2 hours. So let's go without a video in a purely an audio mode. So I thank Dr. Sharwani for introducing me to the audience. And that introduction was enough to prove I'm a beginner for quantum computing. Okay, so, we are all almost on the same boat, except there are some exceptions. Okay, let us not consider them significantly. Quite a few members in this crowd, you are already practicing quantum computing science and quantum computing programming for your research works or so. Overall, I come from classical computing background. That's not because I was not interested, because there was no opportunity to look into any of these domains that time when I was doing my master's or PhD. Even though I was at IISc and Dr. Apurva's lab was quite active in uh, doing quantum computing research, but still that was far reach for us. Okay. So we were pretty comfortable with programming and other stuff. Okay, so that's why normally we chose networks was the very popular domain that time. So my interest was on network security. Of late, I kind of planted into this domain, rather came into this domain. So that's fine. Okay, that's a chance. That's a chance or an opportunity. Everyone, one or the other way, we should get to start looking into new subjects and feel ourselves energized and feel ourselves motivated. So, with that enthusiasm, I'm trying to present my understanding of the subject. I am since the past 3 days. It was all high-end sessions in quantum algorithms and physics and maths part. I may not be repeating that stuff. I thought, okay, let me share a kind of recap or a kind of revision of the concepts according to my viewpoint. Maybe that was going to be helpful for your facing tomorrow's assessment also, because these 3 days content, you need to have some one repetition on that probably. Without I go into any of the details, because it is very difficult to, because you already went through 18 hours of sessions roughly, so it's not possible to touch upon 18 hours of content, whatever it is. That's why I thought let me also include in my presentation not purely on machine learning, even though I come from AI and machine learning background, which is classical underlined. Okay, you need to make a point on that. So quantum machine learning is a new field for me also. Seriously, I'm not designed any circuits on this. I'm or algorithms on it. I'm just trying to pick up the required fundamentals and trying to make myself comfortable. And my suggestions to many of you present, you are quite experienced. Some of you are quite experienced people and enthusiastic. I wish whenever there's an opportunity comes on talking this kind of subjects, do not hesitate to take it up, because that's very important. That will make us to study a lot and trying to make our concept clear. Otherwise, we kind of stop this study here only after 5 days, and again look for one more FDP to come up just for a mere collection of certificates. That definitely doesn't help. That's why whenever there's an opportunity in your institutes, try to form small clubs, because quantum computing may not attract large crowd in the beginning because of various reasons. You may not be having a technology support, infrastructure support. We are also like that. We do not have any specialized equipments at RVCE for experimenting on quantum computing, or so we are also depending on the quantum computing infrastructure outside on cloud. So that is a state of the art at Indian scenario is considered in terms of except IITs and IAC and other premier institutes and some specialized schools and universities. They have started working on quantum computing infrastructure development. That is also in a minimum level. I think yesterday, the very day when Apurva was mentioning about just 2 qubits and 3 qubits kind of realizations are also quite difficult in Indian level. So in the world level itself is a 50 plus 60 plus kind of qubits are running, and a practical implementations. India is far behind in terms of realizing the quantum hardware. Let us not go on to talking some bureaucratic aspects now. We shall look into the subject. So as I proceed further, I try to touch upon some of the, in fact, I organized my presentation. I'm not kind of, seriously prepared for this presentation because I was kind of occupied for all 3 days on sitting through the sessions and learning. Like you, I was also learning how many times we listen to the experts. It's not enough in quantum computing domain. So that's why I thought of making the presentation bit light and try to be kind of interactive here and there. Maybe I'll throw some questions to you. You try to Google it and try to put your answers in the chat box and so on. Let us see how can we make the whole session a little interactive. Few assumptions. First assumption is you're all sitting in front of your systems. Okay, very weird kind of assumption because FDP is such a opportunity to keep us away from regular classes and also other commitments. But I wish at least pay focus on 50% or 60% of the content what is kind of delivered. My second assumption is I am a student. I am nowhere an expert in this domain. So I'm just doing my kind of preparation for the research. In a research training program, we spend at least 1.5 years and 2 years for preparing for a subject. We started these activities roughly a year back and 16, 18 months back, just as an interest group getting formulated. And we struggled a lot, making one group and bringing up to this stage. Okay, so we want to do a lot. So industries are also not kind of have a confidence on faculty. If I go and tell industry I can do something in quantum, they look us suspiciously whether they can do. That's the scenario now. But we are persistently behind trying to reach industry and trying to bring them and trying to create some kind of confidence with them and all. Okay, that's the thing. That's why I do not consider myself anywhere in the expert. I'm also start picking up the subject and reading wherever the possibility is there, trying to understand the topics. That's the way one should start. Do not worry. People were expressing we are not following a lot of things in this subject. Do not worry. It happens. It happens for good. Okay. My third question is, how many of you got quantum dreams? Okay, so it's a thing like when you are sleeping at night, sitting through all the sessions seriously, you might be seeing qubits, superpositions, okay, entanglements, okay. So I will show you some interesting TEDx talks in the break for kind of give you an idea what and all people are crazily thinking about this quantum computing domain. So it's a transformation time for quantum enthusiasts, even though you come from, or we come from, or I come from any classical background. And if you are good at physics and like physics, uh, it's not like everything of quantum mechanics you should know to do quantum computing and all. We are not developing technologies, we are using technologies. So using technology is, like yesterday and day before yesterday, you're looking like you are writing a Python code and using quantum computers. It's just like using an API for all the gates and all the transformations you're doing on the qubits and all this stuff, right? So as a technology, we are not doing any research activities in that line, and we are, of course, going step by step, baby steps we are taking. So there are a few assumptions. Let me start with a quote. Welcome to the world of quantum computing. This is Professor Savas Dimopoulos, particle physicist at Stanford University. One of his statements, he says, the thing that differentiates scientists is purely on artistic ability to discern what is a good idea, what is a beautiful idea, what is worth spending time on, and most importantly, what is a problem that is sufficiently interesting yet sufficiently difficult. You please follow it up, because we may be in a stage that you start feeling difficulty. When there's a difficulty, there's an interest. Okay, if everything is available easily to us, you will lose that interest. So difficulty, if you are facing difficulty, means your brain started working. So that is what a neuroscience says. So you start thinking rationally, you start finding out what are the avenues to make the whole task simple. This is pachinko machine, was the Japanese term. If you look into the left-hand side of my slide, it gives because you're already 3 days old in quantum computing. I want to take a answer from participants. Sharwani, can you moderate this?
Sure, sir.
Yeah, if someone wants to tell what is this left-hand side figure is doing in the quantum computing perspective, you can unmute. She can sanction you the mic, and please go ahead. If any of you are having interest to speak. Any participants interested?
Or they can put in the chat box also, sir.
Yeah, you can make use of that.
Okay, Kavita ma'am is willing to talk.
Yeah. Please, Kavita.
Yes, sir. 1 second.
Sir?
Can you hear, ma'am?
Hello, sir.
Yeah, Kavita, please go ahead. We can hear you.
Ma'am, Kavita ma'am, we can hear you, ma'am.
I think.
Kavita ma'am.
Okay.
Anybody else?
Hear me?
Yes, ma'am.
Kavita, you must speak. Otherwise, yeah.
Yes. Good morning, sir.
Good morning.
Sir, it is the waveform shows there is a superposition and an entanglement at the end.
No, I'm not talking about the waveform. I'm talking about the left-hand side, the blue box one, the machine. How does it relates to quantum computing realms? Quantum computing. Any idea?
Some answers are coming up, sir. To catch as many balls as machine can, first one. Second one, interference.
Then? Okay, good attempt. Let us not waste a lot of time here. So probably if you connect this to your quantum basics, I could say all these red dots are my qubits, okay, which has been kind of created by some technology, okay. We don't know, there are many ways of creating qubits. They are allowed to move in a free space, in a maybe some kind of control is there, okay. You can just think like that, some kind of control is there, and they are kind of moving towards one convergence point, okay. So during this journey of movement, there would be a lot of interference which happens because the entanglements could happen between the qubits, and they get kind of correlated in a sense, and we are forcing them to come to some convergence, which is the expected superposition forming. So I would say a quantum machine would take some input superposition and kind of transform into an output superposition. In this process, you will be having many technologies coming, and different companies are working on. So this is purely a wave mechanics, right? The quantum is a pure wave mechanics. So every particle is a wave in a sense. Okay, that's why it's called as particle wave duality. So when the waves interfere, you get a highest magnitude for a wave, and that would add upon, and you may get a increased amplitude, or sometimes you would get neutralized. In the sense, not always the wave patterns improvise the amplitude. It could also neutralize. Okay. So this is what we are forcing to do. Okay. And let me give a lot of clarity on this later. So this is a simple transition from classical to quantum computing. Many of the speakers have spoke about this, but I'm going to put up my understanding so that I told you that's why my session is not purely only on ML. I am also going to cover some of these concepts. What is this? Any idea? Can you put up in a chat box? Some answers?
A state machine.
Yeah, it is a state machine. Also
replied.
Oh, okay.
Anybody else?
I can call it as a Turing machine.
Harini ma'am says it's TM. That's Turing machine.
Oh, okay, fine.
And,
so
Nishit sir, mathematical model of computation.
Yeah, all are correct answers. All are correct answers. It's a finite state machine. It's a Turing machine, a kind of concept given by Alan Turing. He has visualized the complete computation as a state transition from a state to the other state over some kind of input, whether you transit a state from QI to QJ, or whether you be there in the same state on your input, and while doing the transition, you may also generate some result. All these things are possible in a finite state machine or a Turing machine. I want to take an answer from you. Is quantum computing follows the Turing machine model? Only binary answer, yes or no. On chart.
Sumati ma'am says yes. Nishit sir says no.
Yes, no.
Yes. No. Sumati ma'am says yes, and Nishit sir says no.
Okay.
Some more answers from audience.
Can you give mic to Nishit?
Sure.
Why did he say no?
Nishit sir, you would like to answer?
Because binary answer means either yes or no. Nothing can be, no one can say maybe. Yeah. Please think on it. Please think on it. I'm telling you, you have all the freedom to browse also parallelly. See that you are looking, keep the tab open and look for the answers. Is this a state?
And Nishit sir says since there is no specific 0 and 1.
Mm-hmm.
And Shabana ma'am asks for, can you repeat the question?
The answer for this diagram is it's a finite state Turing machine. Quantum computing also follows the same model. It's a binary answer question. Think over it. Okay. Yeah, these are all questions I am putting in front of you. Classical computers per se is a general purpose or multi-purpose system which can scale from small level to the large level. It of course operates on a binary information. Some mic is on. Okay, it's a discrete state machine. You can measure the state without any problem at any interval of time. And arithmetic and logical operations are predominantly done in classical computers. Of course, it is based on Boolean algebra and all these and, or, and whatever it is. And no restriction on copying, it is very much deterministic. These are the points on classical computers in a way. I think every one of us will agree on all these points. Okay. Deterministic means what? If you just run a logic over a specific input for a specific purpose, always you generate whatever you're intended for. Okay, you are very much sure of your output. Okay, so classical computers has all these advantages. All these advantages. Where does this fail? That's a question. That's what is the people trying to answer in a different way in a different session. But this is my way of answering. I start to answering this question by giving you a story on the rice and the chessboard. This is the game which was kind of played between a king and a champion of the chess. He assures the person that he'll keep giving, double the rice, double number or two number of grains. Every one box you get twice on the previous. If he gets 1 grain on the first square, 2 on the second, 4 on the third, he agreed for this computation. In never realizing the 14th square, he wants so many number of grains of rice. On the 64th square, he wants 18 followed by 1, 2, 3, 4, 5, 6, 18 zeros grains, which is equal to about 200 billion tons, sufficient to cover the whole territory of India with a meter thick layer of rice. This is an interesting analogy. When there is a problem grows with exponential complexity, the present classical system fails utterly. So we need a power which can handle such an exponential growth of the state space. That's what was discussed also in the previous sessions. This is called a state space explosion, or it's an explosion problem. Okay. There are many problems which falls into this category, like we call them normally as combinatorial optimization problems, like assignment problems, closure problems, CSPs, cutting stock problems, integer programming, knapsack, MST, scheduling problems, TSP, vehicle routing. All these problems easily falls into this category. So the complexity grows exponentially, the requirement of resources grows exponentially, where your classical computers will start doing nothing. It's going to start crumbling. It's going to die after some time. Of course, this was told by many people. The death of Moore's law, we call it as famously, Gordon Moore, the founder of Intel, he has given the Moore's law. He said roughly for every 2 years, the digital electronics, doubles, the complexity and performance doubles. The prediction says about 2025, the lithographic miniaturization technology, silicon lithography has going to kind of saturate, where there would not be an improvement in terms of processor architectures. But do we have the problems for such a high-end architectures? That's also a question now. Why people are behind quantum computing? We have enough infrastructure around us. People talk about billions of dollars have been spent on infrastructure building, everything. The ITRS, International Technology Roadmap for Semiconductors, which has tracked the complete development of the silicon technology, it has projected no improvements beyond 2021. Maybe that's the kind of projection the people are giving. If this is the situation, is it possible that everything, whatever is happening in on the classical infrastructures or the classical computers, can it be directly go from 2022 onwards to the quantum computers? Any answer? Binary answer? Yes or no? Is it possible to move everything onto quantum computers? No. Yes. I could see the chart now. It is definitely not possible. You can't use a quantum computers for equivalent to Shabana says not immediately. Yes, of course, because quantum computing is still in its infancy and people are just doing some kind of building quantum computers, and most of these quantum computers are noisy, and they have a, of course, people talk about 50 qubits, 60 qubits, 100 qubits capacity, which is much more than required to solve many problems. But quantum computing cannot be the replacement for classical. There are problems which are suitable only for classical. You can't do C is equal to A plus B with quantum computer. Then what for the quantum computer is good? That's a question that should ring in our mind. Okay, that's what is the whole idea behind this. So industries are looking the alternatives. So one of the alternatives they have projected is quantum technology development. Second alternative they have looked into is they looked seriously into the periodic table, the silicon column, and trying to find out some more material for fabrication, because already the transistors have reached, the size of the transistor. Any guess of the size of the transistors today? Can someone put a short answer? What would be the size of the transistor today? You may browse, okay, you may browse. You may spend 1 or 2 minutes, one minute, no problem, because let us learn something, few things also, but let us have an understanding on it. Okay, any idea?
45 nm.
Yeah, it has kind of reached to the nanometer scale. Roughly, if you look into the size of the transistor, which is hundreds of times less than the RBC, red blood cells. Okay, it is, what is the impact of this? Why can't we keep reducing the size of the transistor further? Because Intel itself has accepted, okay, Intel itself has accepted they are generations behind than AMD. The AMD is doing a lot of research in reducing this transistor size now. They're trying now 5 nanometers, 7 nanometers kind of, fabrications. they're saying we can't achieve this much of miniaturization. The reason is when you keep achieving a lot of miniaturization, the electrons, okay, the electrons will start crossing the barrier. That would lead to a lot of noise on the CPU logic itself. So there are a lot of constraints in terms of, miniaturizing further. That's why they look for the alternative technologies like quantum. Second one is they look for more material science. That's why material research is picking up a lot in a IT space. And third alternative is, of course, optimizations in algorithms. So algorithm optimizations will definitely going to pick up one more booming domain now in the coming decade. Whatever the algorithms people have developed now, which are on a classical side, which are not optimized, they will get into the optimization phase, and because capacities are going to be reduced. Okay, yeah. This I'm not going to talk. Yesterday, Dina and Archita has spoke a lot about this time complexity classes. You see, today we have far reach than the problem space. Like we were just talking about P and P complete and all. Now we talk about P space. Okay, P space is a polynomial space. In that we have a BPP and BQP kind of solution space, which are purely quantum. BQP is purely quantum polynomial time, but it is probabilistic by nature. That means you will get the right answer with some probability. That's why the quantum computing, many of the problems which are NP earlier, they have become P because of the BPP kind of algorithms which have come up. Yesterday we looked into Grover's algorithm, we looked into Shor's algorithm, prime factorization, and you looked into the searching algorithms. You look into these algorithms, they try to do a lot of searching activity. Okay, that's where, yesterday Arpita also was talking about QKD. QKD is more of searching the state of the key which is exchanged. Normally in a classical kind of cryptography, the key has been exchanged between the two ends. If someone gets the right hold of the key, he can go for encrypting or decrypting things. What is the threat in this domain is, if someone, let us assume that between two organizations, a classical crypto is working, the intruder will be having quantum infrastructure with him. If he gets hold of the classical key, he can do within seconds, he will reveal that key. It is basically a quantum computing based attack. It's not, if you change a bit to a qubit, your cryptographic system will not become secure. It is not that way. The problem is not that way. We are still we need to depend upon classical channels for transmission, but quantum channel concept has come. Now that's why China is also pioneering, and they are laid out thousands of kilometers of quantum channels, quantum repeaters, quantum bridges. All these things have come up in the networking. Quantum networking is one of the quantum communications, one of the booming field, where we talk about teleportation and Bell state transmission, and a lot of that stuff is available on that side. Importantly, we should know, if we are not going to change our classical communication, secure communication to quantum side communication in near future, maybe 5 years down the line or 10 years down the line. That's why it's all vision technology. It's called as a vision technology. It is not an immediate, you can get the benefit of it. Okay. So in future, if someone start giving the quantum computing power to the third parties, they start harnessing this power and try to break all our crypto systems, and that would lead to a national security problem. Okay, so that's the reason there is a lot of buzz around quantum cryptography. So of course, this is a pretty straight answer why classical computing is slow. every process is most of the time it is sequential by nature. Even though you parallelize your computing, but all the parallel parts would work again sequentially. It's like, you have a sequential logic, you have split into multiple processors, but once it goes into the logic, again it goes into sequential way. And this is not enough to tackle problems of higher scales. One of the problem is given there. Imagine if you need to simulate how a protein molecule would behave in water for 1 second. It seems a fairly small problem, but with a modern compute and efficient algorithms, it would take months to compute the results. This is the kind of problem quantum computing has to solve. Okay, quantum computing is not to do a word processing or statistical analysis. It is not going to design for that. We have research problems. We have problems which are taking in a classical world, years and months, that can be kind of transformed into problems which can be solved in minutes and days. That's where we get a speed up advantage in quantum computing. Okay. So quantum computing in a nutshell, it's a high speed parallel computer. You are depending on quantum bits. I think I don't want to talk about quantum bits here, because quantum bits we are talking from past 3 days. They are the information storage. They work as information storage and processing units. In quantum computing, information itself is physical. Okay, that's the difference between a classical to quantum. When you say qubit, it's some physical entity. Okay, either it's an electronic level, whether it is a molecular level, whether it is an ion level. You have a physics everywhere, and it has a interesting characteristic of showing infinite number of states at the same time. The information can be in infinite number of states. As you increase the number of qubits, you get a very large state space, and you will be keeping the information in all the states parallelly. Of course, you have a quantum logical operations. You'd seen yesterday, you have X gate, Y gate, Z gate, Hadamard gate, C0 gate, swap gate, many of these, logical operations which you are using to operate with the qubit state. Okay, so making a superposition of the qubits, making the swapping the qubit state, and a lot of binary operators or unary operators. All these things are used for developing the quantum programming. It's based on physics fundamentals. I will be touching a bit on physics also. That's very essential, and also of course linear algebra, because it's purely a vector space, Hilbert space model, where you have everything is represented as a vector, eigenvectors and eigenvalues, and it is a probabilistic by nature. The results are probabilistic. You are purely depending on probability. That's what you see in your Dirac notation or Ket notation. You have alpha times 0 plus beta times 1. These amplitudes, or when you square it, and you will get a probability equal to 1. So it is probabilistic by nature. And of course, it is one technology where strictly no copying. So when there is no copying, you are safe. That means you are there for security domain. If you restrict people to copy, if copying will affect the state, you get to know that if someone is copying, like in a test, hundreds of students are sitting and writing. Imagine all hundreds will be in 100 qubits. Okay, all are in their own state. If someone is copying, immediately you will understand. Okay, then that is what is required. Nowadays it's not possible. If you increase it to 1,000 students, I want to have one solution for identifying. Someone has copied, I'm talking about a different mechanism. Even though example is naive, I'm not connecting it straight away. I'm just telling you the cloning or copying is strictly forbidden because of the particle wave duality, and the interference will break. And once the measurement happens, it collapses to one state from the superposition state, and all those things are possible. Okay. So on my slide, on the top right corner, there is a picture. Can someone guess what is this picture? Don't tell me quantum computer. I want to tell which quantum computer by which company. IBM, no, IBM is displayed here, the down. IBM quantum computer and a Google quantum computer looks like a golden chandelier, which is a zoomer. Any answer coming up other than IBM? Don't think IBM is the only company working in quantum computing space. We have many companies. Microsoft, D-Wave, Rigetti, IBM. Any answer for this picture?
ZDNet.
No. The answer is, you can browse, if you can see quantum computer in the images of Google. Google, I written there, Google photo I given already.
DVMMC is Intel.
Intel, no, Intel is not in quantum space.
Honeywell.
Honeywell is the right answer.
Harini ma'am. Yeah.
Harini has given the right answer. Honeywell is a company, their quantum computer looks like that. It is an ion trap quantum computing system. Strange, no? It just looks like some machine. Everything, quantum computer has a different look. Altogether, they're in a very near absolute zero temperature because of various reasons. Yes, moving further. A bit of physics now. Maybe I'm not a physicist by degree or by study. I never looked at physics so seriously earlier. During my 10th, 11th, 12th, I did some physics, and later, I don't know, I don't remember whatever I studied during my BE program, first year physics. Later on, so far, no physics. But okay, computer science people should know maths part. I used maths during anybody should use maths during the research timings, like depending upon the research field, maths also will come along with you. Physics is a natural science which involves the study of matter, motion, behavior through space and time. This is a general definition of physics, but it's interesting. Classical physics is causal. That means if you want to predict something about the future, you should know the past. And if you know the present, you can also go back and see what happened in the past. Okay. Metaphysics is philosophical. Okay. Like God, study of notion of existence, concepts of space, time, free will, individual, people talk about Atma, people talk about Gnana, a lot of, all this stuff will come in metaphysics. Quantum physics is another genre. It's a study of quanta. Quanta refers to packets of energy. These quanta are problematic because they are unpredictable in behavior and movement, as they have qualities of both particles and waves. Here, what we are targeting is the size. Extremely small units which are carrying energy. When the size decrements a lot, they all be in a waveform. Most of the time they will be in a waveform, presenting in different positions with a different probability. Okay, you imagine a waveform. A particle is in a waveform. It is in different positions with different probabilities. The moment you measure that particle to see what is the speed of the particle or what is the other properties, the waveform collapses. Okay, that means it exists in the waveform and it collapses when you do some measurement. Okay, that's called as wave collapse. Then you may think, do you think human is also full of energy? Human body is full of energy? Binary answer, yes or no? Yes, human is also energy. Okay, but we are not quanta. We are of good size. We are of different weights, and we are considerably bigger. When you increase the size of the matter, the wavelength decreases. When you decrease the size of the matter, the wavelength increases. It is a indirectly proportional quantities. Okay, when that is the case, we are supposed to deal with waves when we are dealing with a quantum physics level. Okay, that's where the complete challenge comes into. That's why the quantum physics is the wave physics. We are dealing with waves. Of course, I do not want to spend a lot of time here. This is Newtonian mechanics. It talks about the particle, the indivisible mass point object. A system is a collection of particles. The state of a system is a collection of the states. This is what Newton said in the beginning. And also he said very clearly, every particle has a trajectory. Okay, there's a point you should know. Every particle should have a trajectory for motion. Okay. Light is a life for us. Okay, light, without light we can't live. Light is an energy, light is a radiation, light is a photon. Light itself is a dual nature, which means it is a particle and both, because it's comprised of photons. Of course, this is a theory. Newton has stated, Isaac Newton has stated a theory called corpuscles theory. It was actually defeated by other physicists at that time. In 1678, Huygens proposed a model where each point on a wave front may be degraded as source of waves expanding from that point. Max Planck has proposed the radiation comes in discrete quantities and quanta. So the entire credit goes to Max Planck in 1900, okay, stating the radiation comes from the discrete quantities called quanta. What is the state of the art today is, these photons, which are the finer particles, people are developing technologies to work with these photons. We have a hardware called single photon generators. You can generate a single photon with a hardware. That is, of course, a very costly hardware, which people are using in the high-end universities for doing research in quantum computing and also in bigger industries. And people use hardware to split the photon. Of course, polarizers and all very cheap equipments that you can find out in any engineering labs, where you can adjust the polarization angle and all these things. But handling something at the photonic level, you need a special equipments, but researchers are doing a job already on that. So the single photon technology is the backbone of a future quantum internet. Okay, then of course one statement by Alan McGill, you can get into trouble if you give the photon too much reality. You just think on this statement. There's a big article on it. Okay, photon is the fundamental unit, if you say. Of course, there are many other ways of creating the qubits, but I'm telling you, if that is the case, when the too much reality is sanctioned to the photon, you yourself get in trouble. It's equivalent to saying, if AI becomes super intelligent, it's a threat for the human. Okay, a lot of job will be cut down, curtailed with a specialized super intelligent AI. This is Newtonian mechanics. It's also called as classical mechanics. He said very clearly an object is limited to a place, limited to a time. Okay, and large objects, and he said it cannot approach the speed of light and all this stuff. Okay, let me not spend on that. Quantum mechanics is the understanding of how physics of the smallest particles in the smallest spaces operate. This is quantum mechanics. We are dealing with the physics of smallest particles. And in the quantum mechanics, probability is the leader. Probability is the king. That means these objects will be in a haze of probability. That means predicting the chance of an object at a point A from a point B is a probabilistic measure. And this is guided by wave-particle duality. As I already mentioned, I'll show you one or two illustrative slides. And also the uncertainty principle. Okay, these are the two basic things. Probably the earlier speakers might have not told this with a lot of emphasis. I am trying to emphasize that. Okay, so without knowing these terminologies, first of all, you should start appreciating physics. Then you slowly transfer yourself into digital part and slowly transfer into a quantum computing part. Okay, that's a stage of learning actually. Even in the machine learning also. You should know classical machine learning, then you start appreciating why quantum machine learning is required. Otherwise, it's not a QML, is not a new domain which is apart from whatever you've seen in the last 3 days. QML is also something like that. Okay, we are developing a quantum circuits for a machine learning purpose. Okay, so as of now, we do not have something like whatever the classical machine learning is there, we are transforming into quantum machine learning. Whatever the KNN is there in classical, QKNN in quantum. Decision tree is there in the quantum classical, quantum decision tree is there in quantum. Okay, you can think quantum SVM is there, quantum SVM is there. Okay, it is all a kind of transformation people are doing. Okay, so you should know one or two examples how the people are really working on it. That will become an interesting use case for you for studying further. Of course, one of the important constant which plays a quite role in quantum mechanics is the Planck constant. Okay, you see the order I given in the below figure. That's the quant of energy, joules per second. That's the quant of energy. Every propositions, every relations given by the physicist involves this constant. This is quite famous experiment by Heisenberg, which is called Heisenberg uncertainty principle. He states for a particle, if you measure the position, it is impossible to measure its momentum. If you measure the momentum, the position cannot be measured. I think you can see in the right hand side, I would try to capture some media files from the internet to show you give you an idea of how the trajectory is building about for a particle. They are called as delta x, delta p is greater or equal to reduced Planck constant by 2. There's an inequality between the left hand side and right hand side. There's always an inequality. If you raise one value, the other value will shrink. If you raise the second parameter, the first parameter would shrink. Always this inequality is maintained. This is the basis for your QKD also, quantum key distribution, quantum cryptography. Okay, we use Heisenberg uncertainty principle for that purpose. Okay, it's a of course, this is what is the principle set by Heisenberg, and it has tried the Newtonian trajectory principle. Okay. Of course, this correspondence principle by Niels Bohr and all. Let me not go on it. Particle wave duality That means this is very simple thing. It says that sometimes the particles behaves like a classical wave. In some other experiment, it behaves like a particle. See, that's why quantum computing is mystic. Quantum computing is a full of wonders. In the sense, it's like an Alice in Wonderland kind of concept. There are many theories in quantum mechanics still do not have a proof from the physicist, but it happens. It happens. I'll show you that. It happens. Physicists have made a lot of attempt to prove it, but they failed it. But they just accepted it is going to happen like that. That's the nature. That's the God. That's a which is given to us. You need to accept it without questioning it. That's what is the quantum mechanics all about. You're trying to you make a best use of that in your computation requirements. Okay. Is Mr. Maxwell, he talks about electromagnetic radiation can explain these two phenomena, which was the reason why the corpuscular theory proposed by Newton has been abandoned because of this duality principle. This is particle wave duality. You can see this is a famous double slit experiment. Probably Trivikram has gave you some idea of it. Just quick revision on that. See, I'm telling you, at the end of this FDP, definitely you should remember all these terminologies. That gives you, okay, I heard about Heisenberg uncertainty principle, I heard about particle wave duality, I heard about, wave position, all these things, that's very important to know. So in this case, you see there is a wave source, there are two slits, there's a screen in the background. You see the fringe pattern getting formulated. If it is a particle source, you are throwing the particles through double slits, you will see two lines getting formulated on the screen. If it's a light source, okay, you get a light and dark fringes, okay. If it's an electron source, you still get on the screen fringes. These fringes which are getting formulated are called as interference pattern. That means electrons or particles, when they move through a double slit, you get a wave pattern because light is a wave. So you get a wave pattern and you get an interference pattern on the screen. So electron behaves like a wave. This is what is called as a duality. When this duality breaks is when you have electrons, you are passing through double slit. If you do not have any observers, nobody is observing what is happening, it forms an interference pattern. If you put some observers, some recorders, some measurement, this wave collapses, it becomes particle. This has been experimentally proved by using double slit experiment. Okay, double slit experiment is all about this. You have the wave pattern formulated by electrons when there is no observer or no measurement. This wave pattern collapses to particle when you put the observer. Okay, I hope you got this point. I think we are kind of finished 1 hour now. I want to show you one small clip as a refresher. Do not ask me, is it directly related to my discussion, but I would like to show you for my satisfaction. I like Sharwani to tell me if the file is visible. Okay.
Yes, sir.
Okay. I'll share this. Now I'm playing. Okay. I think, is it loading, Sharwani?
Yes, sir. It's loading.
Okay. Have a break for 2 minutes watching this video. That's okay. Still loading.
I think it's taking some time, sir.
Okay.
Uh,
Is it audible, Sharwani?
no, sir, it's not visible. The video is not loaded here. I can hear some sound coming from that, but video is not seen. Yeah, now yes, we can see that.
Sharwani, is it okay?
Yes, yes, sir.
I'll replay the video. Yes, I think that's a small relax for all of you. I hope my screen is visible.
Yes, sir.
This is a trailer from the movie, okay, Flash, where they spoke about utilizing quantum computers. Of course, this is much beyond quantum computers. He has prepared a superhuman with a super intelligence kind of model. Okay, so he will be using in the background the quantum computers. So that was the idea of the movie. Okay, is all logic has been processed with the quantum computers. That was the illusion or some thought. That's where we are supposed to be today. So real quantum computing is all about. I shown you this slide during my inauguration session. The precursor is from Richard Feynman in 1981. Okay, so he talked about can we simulate physics on a computer, and not all of physics. Okay, not all of that physics. We can build a quantum mechanical computer as an answer to the notion given by him. This is Professor Alan Kay, who is a computer scientist. Okay, so he has given an interesting difference between natural sciences and computer science. In natural sciences, nature has given us the world and we just discovered the laws. In computers, we can stuff the laws into it and create the world. Experiments in quantum physics are now creating artificial physical systems which obey the laws of quantum mechanics but do not exist in nature under normal conditions. That's why quantum computers sits in a super cold, temperature, which normally it's not a normal condition for working for it. That has been not realized yet. We can't see a desktop quantum computers or desktop or handheld quantum computers and all because it is an against to the normal law of nature. So we are dealing with particles at that level. So this is about quantum computing. I do not go into a lot of details because people have given you quite a lot of information here. Just for completeness purpose, it is a study of information processing tasks which can be accomplished using quantum mechanical systems. Remember, quantum computing is full of quantum mechanical systems. We have infrastructure in the backend which works with quantum mechanics. And qubit is the game changer, which is the unit of information. Then mystical phenomena like superpowers in terms of superposition and a lot of stuff happens in quantum world. This is an interesting analogy of a tossing a coin. Normally people use this analogy of a tossing a coin. I have a question for you, for the audience. When you toss a coin, the coin is in the air, you call the coin is in superposition? You think the coin is in superposition?
Shabana says yes.
I want to take few more responses. It's a binary answer, that's why.
Nishit sir says no, yes. So many yes and no's are coming, sir.
I want you to tell how many, maximum is what, yes or no?
Yes or more. Nishit sir says no again.
Okay. Can you give a mic to one of the person who said no? I want them to speak.
Nishit sir, I don't know whether he's willing to answer. Can I enable your audio, sir?
Or you can ask them to raise a hand and also.
Yeah, you can raise your hand. And just... Kavita ma'am, you would like to answer? Kavita ma'am, you would like to answer?
Yes, ma'am. Sir,
sure.
it is like it is in a superposition state because we can see both the head and tail popping up at the same time.
Is it at the same time?
Yeah. When it is in the air.
Is it possible a coin can have head and tail on the same time? If it is going in a hypersonic speed of spinning, okay, just think like that. If it is in a hypersonic, the maximum whatever you have in the world, if a spins with that force, you are saying you can see both head and tail almost in the same position, same level. Has some influence in terms of the speed the coin has been tossed? So, yeah, please go ahead if anyone is interested.
Dr. K. Sharma also, sir, want to answer, sir.
Please, sir, please.
Sir, it is in superposition unless we measure it.
Okay. Yes, it is in a superposition unless we measure it. Once it comes onto your hand, it falls either into head or tail. Yeah, do agree. Measurement stops the spinning. That is what is the basics. Okay. So your understand. May I speak, Shabana? Yeah, please go ahead. Shabana, you please unmute Sharwani.
I think she has not raised. Yeah, I'll check for her, sir. 1 second.
She had
Shabana ma'am. Yeah, 1 second, sir.
Shabana or
Spelling SH.
yeah, probably. Let's see.
Shra.
Shabana. I
Yes,
want
sir.
to give
I'll
the
enable. I'll unmute her.
Shabana,
Yes,
SHRK.
sir. I've done it, sir.
Shabana, please go ahead. Your mic
Shabana,
is-
ma'am. Shabana, ma'am. Not responding, sir.
Okay, okay. Any others want to speak? Yeah, this is a quiz question, good question. Okay, the answers you guys gave us, the coin is in, if someone says no, I want to listen from them. Both of them said yes for superposition. If someone said no, they are not in superposition. If anybody wants to kind of pitch in and tell why it is no? There's equal probability landing in any one state. That is Shabana said no. That is why she said unequal probability of landing in any one of the state. Accepting the coin is not biased. We have an equal probability. Otherwise, the coin is biased. Deterministic probability is pre-decided. Probability, of course, changes. You know, if you keep doing, that is the beauty of the probabilistic experiments, right? You keep repeating the experiments for that's why I call it shots. I think you were talking about shots and all. Because quantum itself is a probabilistic phenomena. If you keep repeating the experiment again and again, the probability values would definitely change. The number of hits you are getting is not always, of course, in terms of number of experiments I'm talking about. I'm not talking about whether you get head or tail with a 0.5 probability. If you increase the number of events, definitely the number of times you get head is not equal to the number of times you get the tail. So when in the air, there are two theories, whether it is equally possible to have an undeterministic state. The coin is in a probabilistic state, like a qubit, it is just spinning, and it can be in any of these states with a different probability. That's an answer. This has been kind of proven by Erwin Schrödinger, his famous cat experiment. I think people have mentioned here and there Erwin Schrödinger in 1935. He conducted a cat experiment. Of course, I wish you people can look into Schrödinger's cat experiment. He takes a box and put a cat inside and put a mechanism of killing the cat with a probability of 1/2. And he closes the box and he leaves the cat for some time. And the chance of killing the cat is 0.5. By sitting at outside, how you can really think whether the cat is dead or alive. Okay, that is kind of expressed in a quantum superposition state, where 1/√2 times the cat is alive and 1/√2 times the cat is dead. That means the cat is in the wave form. Okay, it can either exist in a dead state or live state when it is the box is closed. When you open the box, the moment you open the box, you're measuring, you will see the cat is dead or alive. So that is the final measurement you get. That means unless you measure, the object is in its superposition state. Okay. This has resulted in one of the famous equation of by Schrödinger. Is called as Schrödinger's equation of total energy, where he divides this equation over the wave function psi of r with an energy multiplied by psi of r equal to the potential energy plus kinetic energy. And this is a time independent equation. There is no time factor here. So time is not going to play any role in this equation. And in 1930s, around 1930s, Schrödinger got a Nobel Award, Nobel Prize for this equation. One simple equation getting a Nobel Prize is a big achievement. the down the Schrodinger's photograph is the wave formation of a particle, how the particle inside the box. If you put an electron in the place of a cat, you put an electron into the box and close the box. The electron moves in a wavy wave format with a different amplitudes. The moment you measure the wave, it collapses to the probability. Okay, probability is an outcome of a measurement. Okay, so these are all the concepts. Okay, I'm making you to kind of a revision. So it's quite important. Of course, this is known to you. Classical computers are quite hungry for memory. A lot of memory requirement in terms of storage space. For example, if you look into the bottom right, the bottom side of the slide, you have suppose to store a 16 classical states. How many bits we want? 16 classical states. Can anybody answer me in the chat box? How many bits you want to store 16 classical states? 4. Any other answers? It's a quite simple question. Is 64 is the correct answer. Why 64? You have 4 bits, 16 combinations, right? Normally your thinking is at any point of time you only think 4-bit state. You always calculate in mind, okay, 16 means 2 to the power of 4, 4 is enough. With that 4, you can represent only one state at that particular time. You can't represent 16 states. When you want to have a 16 states with you, you need to have 64 bits with you. Okay, that is the shoot up. As the complexity increases, as you increase the state space, as you increase the number of variables in the phenomena, your requirement of storage shoots exponentially, right? That's the problem with another problem with classical side. There comes a qubit where you look into the superposition theory. Okay, with only 4 bits, you can manage the 16 combination because you need not require to go for maintaining the 16 different states. One combination of 4 bits is enough to maintain 16 states. Okay. I will not be talking about quantum bits and all. This is a little time taking for me. Quantum bits, just to give an idea, one of the recent project by Google called Bristol Cone, 72 qubits. You look at the number of states they have achieved. 4, 7 followed by 1, 2, 3, 4, 5, 6, 18 plus 2, 20 zeros. That is the kind of state space they got with 72 qubits. Google climbed the quantum supremacy with this, with a pseudo random number generation and all. And Blocksphere, I think Aber has given a lot of details on Blocksphere, which is a 3D space vector representation. We make use of Jones calculus. If you can study something on Jones calculus, there are 6 different types of vectors we can use for representing this superposition thing and all. And Dirac notation you had seen earlier, where the magnitude A magnitude type 0 plus B magnitude type 1 and all. Qubit controls, I think Tribikram has given some idea on this. We have ion traps, optical traps, quantum dots, semiconductor impurities, superconducting circuits. Whatever you were working with yesterday, IBM Qiskit, IBM Q works on superconducting circuits. They work on electrons level, okay, with a very low temperature models. Optical quantum dots are also going to be a kind of very interesting experiments people are conducting. Ion traps are used by Honeywell for using. This is superposition power. Superposition is another theory. Okay. Now, the entanglement part has been kind of a very interesting one, which is given by Albert Einstein, called it as a spooky accelerated distance. Okay, EPR paradox we call it as, where Albert Einstein, Podolsky and Rosen has tried to prove there's a thing called entanglement in quantum world. Okay, I'm not going to do this. This is an entanglement concept where when the two electrons are kind of kept without a boundary of a distance, if you measure the state of one electron, the other one will be having the opposite measurement. This is called as the entanglement theory. So Einstein doesn't believe this, and he used something called EPR paradox called thought experiment, they call it as. That is to kind of disprove there's nothing like no communication is possible beyond the speed of light, because that is extreme communication, right? Extreme speed communication. So people are doing many experiments now. You look into the Chinese physicist, they are doing quantum entanglement at least 3 trillion meters per second. 3 trillion meters per second, 4 orders of magnitude faster than the speed of light. People are already working on how to reach the state to other side with a faster than light kind of communication. This is quite unimaginable. And of course, quantum mechanics is will not keep any belief on causality, locality, realism, and all. Okay, so all these terminologies are quite important from the perspective of quantum mechanics. So this is the final thing in the quantum computing side. Later I'll jump on to brief introduction to machine learning part. The interference, as I told you, double slit experiment, I already told you. What is the role of interference is, this is going to give you the final possible solution to a problem. After a series of superposition entanglement operation, what finally you do in a quantum circuit is, you keep doing some kind of superposition using gates, you keep building some entanglements, and that would form a pattern which will say that this is the solution which you get from the quantum experiment. So the art of designing quantum algorithm lies in designing an interference that increases the probability of measuring a state that encodes a solution. Your interference is the state. Interference is a state. So when the waves interference, either the amplitude increases or it collapses or it will neutralizes. If you take a Grover's algorithm, how do they do search in a quadratic time is because if you start searching in a large search space, you are searching all the entries in a superposition way. And you try to control this interference by cleverly manipulating these amplitudes. That's what happens in a quantum circuit. You're cleverly going to kind of manipulate these amplitudes so that you can get your required solutions. I don't do this industry perspective. There are a lot of works which are happening in. I wish you should see this BMW website. Kindly go into this website, exploring industrial use cases in the BMW Group Quantum Computing Challenge. They have given, in the interest of time, I'm not doing it. You look into the details given in the website. They are given use cases as a challenge for a people to propose a quantum computing solution. Okay, so very, very interesting challenges are there. Of course, basics of algorithm I will not do because algorithms, okay. So I jump on to machine learning, because why I gave this idea is to kind of, it helps you to get your understanding, and some places you may be missed some information due to many reasons. I thought of giving you some idea of a quantum physics and a quantum computing per se, and because I have not discussed any serious maths and that part. That definitely you explore when you go back to the fundamental applying algorithms for solving some applications. You need to understand how each of these operator works, okay, in terms of the unitary transformation. That's why quantum computing is a reversible process, right? Where a reversible process states, if you take the inner products of the vectors in the Hilbert space, what happens after transformation, before transformation, the product never changes. So that is the philosophy of reversibility. Okay, that's an advantage the quantum computing has over the classical computing, where it suffers the reversibility. If you given a large number and if you ask to find out factors for that, it is quite difficult challenge. That is going to be a NP kind of scenario, right? So people are looking for solutions to get back get the process of reversibility. So is Arthur Samuel, he said in a famous definition of ML, the field of study which gives computers the ability to learn without being explicitly programmed. Okay, that's the definition. I think many of us heard about, I keep that assumption in my mind. ML is not a new thing for all of us. So ML algorithms are pretty like this. You have some training data, you have some learning algorithm, you have some answer coming up, you keep doing some query, right? So this is the training part and query part in ML. Normally, you just keep creating the knowledge in by training the model, and the knowledge gets created, and you keep finding out, answering, questioning the machine, you getting some answers predicted, and all these stuff. So this answer will generate out of the learning happened by the algorithm. Okay, so that is the core of an ML algorithm. So ML algorithm always try to accumulate the knowledge out of the training. Okay, it's a different subject. Not going in detail. Okay, ML itself is AI and ML is a different subject altogether. So that is out of scope of context here. We are not doing. We are planning to in the coming sequence. The detailed workshop on QML and ML. That time, those who are interested can please get into that. So normally ML has two parts, static part and dynamic part, where the static part algorithm is responsible for finalizing the optimal behavior to solve the problem. The dynamic part is for processing the behaviors and all, because it's a machine learning. It's like a equivalent to human. Okay, we learn for exhibiting the behavior, correct? So any machine learning output is a behavioral exhibition. If you, how do you prove you have learned? You prove you have learned by exhibiting some behavior. So that's the fundamentals there. Normally, we categorize into supervised, unsupervised, and reinforcement models. This is the classification. I will not go into this in detail. Just these are the categories of supervised, unsupervised, reinforcement. They are all the categories of learning. Supervised, in a one line, supervised means as a teacher, it's a teacher-centric learning. You train the model with a specific IO pairs, and you keep testing the model whether it has learned. In unsupervised learning, you will not train the model, you will allow the model to learn on its own, and behaviors will be learned by itself, by the model itself. You have all your deep learning models like CNNs and autoencoders and GANs, and all these stuff comes under unsupervised category. And the third category is the reinforcement learning, where you are going to introduce a concept called rewarding for every learning outcome. We call it as a temporal learning rewards and credit assignments, and rewards will be assigned for every good move, and punishments are given for every bad move or a bad learning. So the model learns over the time, and is a lifelong learning model. Reinforcement learning is something human being is actually mostly in these two categories: unsupervised learning and reinforcement learning. So we follow, our brain follows only these two categories of learning. Okay, and of course, let me not quantum advantages. Let us look into when you bring quantum computing into the machine learning space, what advantages we get. Okay, See, I'm not going into show you any circuit, quantum circuit. The next speaker will be showing you some cases and examples. Okay, you may be talking about some models also. So I want to set a background for that. So actually these things I touch upon. One is we have something called HSP. This is a hidden subgroup problem. It's called HSP. Whatever the quantum algorithms you had seen, Simons, Shor's, Gross, Bunsen-Weisrani, Dai-Josa, they're all algorithms which one or the other way follows the HSP generalization. So it's a group and subgroup concept, and you can read that statement. I'm leaving there for a second. It's a generalization of quantum computation group structure. It implicit that more difficult problems might be solved by considering various groups and functions to find new algorithms which are exponentially faster than their classical counterparts. That is the notion of HSG. In quantum machine learning, why it is a field of study today is because of the big data. The data size is growing enormously, and the companies are investing a lot in leveraging this data for their day-to-day business requirement. That's why the machine learning is booming. And other advantage of quantum machine learning or quantum, we call it as a quantum decision function, a quantum strategy. It is basically, we want to make some optimization. Quantum machine learning is an optimizer, developing an optimizer for a given problem. Okay, let me put that way. In the sense, you have a problem which is of exponential complexity, and a problem state space grows exponentially. The data variables also grows exponentially. You want to do some kind of strategy over this fast growing state space. We need a system which represent this state space in a minimum number of bits so that I can make some strategies on it. See, I'm not making some calculations on it. Remember, I'm making a strategies. Strategy is different and calculations are different. Suppose if you look into KNN algorithm, what we do in KNN algorithm, we want to classify the query point to a cluster, whether it is equal to cluster 1, whether it uses the cluster 2, whether it's near to cluster 3. We make use of Euclidean distance, correct? We try to find out if the k is 3, we find out 3 nearest neighbors. If k is equal to 10, we use 10 nearest neighbors to find out to which cluster it falls into. That's what we do. We never do any calculations there in terms of, making some manipulation of data and all. We are trying to make use of the same data without changing its state. That is very important in machine learning. In machine learning per se is such a field where you make use of a data and do something. You will not go and change the data, correct? You look into any machine learning model, whether it's a supervised or unsupervised or reinforcement, you're not going to do a chess playing. You will not go and change the configuration of chessboard. You only make a strategies to win the game, correct? That means what? You have enormous state space. You just think 64 squares chessboard. If you put it in a state space, how many number of states you get in a state space tree? If you want to represent the state space tree in a classical computer, it's not easy. Even solving a simple Rubik cube problem, it's not easy in a classical computer because you're having such a huge state space in front of you. You need a quantum machine learning, superposition theory, which you are using there, that is efficiently represent this enormous state space. This point I want to make it clear. That's why it is not 100% transformed into quantum ML now. For example, I told you Euclidean distance. Euclidean distance is replaced by quantum fidelity now. People are talking about quantum fidelity, the distance between two qubits. That is the deciding factor for quantum quantum KNN algorithm. People are trying to find out what is the distance between qubit 1 and qubit 2 to classify that qubit into the cluster. We want to look into how the qubits have been spaced. That's with a different analogy. The whole analogy is different. Whatever you see in quantum algorithms to a quantum key distribution to the quantum machine learning, your complete viewpoint should change. If you are practicing quantum machine learning, practice only in quantum machine learning. Do not get deviate from here to there. Because you'll get confused. Definitely you'll get confused. If you take QKD, you talk about polarization levels. We talk about noise. We talk about measurements. Okay, we talk about a lot of other stuff, but we talk about QML in a different sense because we play heavily with the superposition theory here. Okay. So as of now, the complete models which are available in the industry, in the higher end, we call it as a variational quantum classifiers, hybrid quantum classifiers. Okay. The trend is now hybridization, in the sense a part of the machine learning is classical and a part of the machine learning is on quantum. This is what Dr. Shesha was mentioning in the very first session. The workflow is like that. It goes from classical machine onto the cloud to the quantum machine as a circuit, then from quantum machine back onto the cloud to you as your classical output. Okay, so it's a pipeline. Basically, still it is not possible to take out the classical component from this particular pipeline. Okay, so the entire stages of machine learning or quantum machine learning, so called as, it's still a classical and quantum. It's a combination because you're dealing with the classical information using quantum system. You're not dealing straight away with the quantum information using classical. A day may come where a quantum information can be dealt with a quantum computer, then you end up in QQ kind of algorithms. That's still a long way to go. Okay, there are a lot of role of classical information systems today. It is prevalent in quantum computing world. So quantum machine learning sits exactly in the intersection part of machine learning and quantum information processing. Okay, what are the challenges here is it lies in finding parameters. Okay, we have in a machine learning world something called model parameters, something called hyperparameters. Okay, for a model, learning parameter. You know, if you go into machine learning and study, it's not easy to build a machine learning model. If you want to make a machine learning model to work, you need to look into all these parameters, free parameters, controlled parameters, okay, model parameters. We call something called the weights, learning rate, okay. Because if you look into classical machine learning, it's all just an optimization problem. If you take a neural network per se, neural network is heavily influenced by Fourier series. It is a derivative, double derivative kind of situation. You keep you have a descent and ascent kind of algorithms, right, to reach a global minima point. Because machine learning is an optimization problem. When you have your machine learned successfully, you have reached the global minima point of your error surface. Okay, you have an error surface, you have reached the global minima point in the learning. To reach this global minima point of error surface, we need to make a lot of these parameters and a lot of initialization should do. That's the biggest challenge the quantum ML is facing. And of course, ML is implemented using same superposition entangle properties. There is no other additional properties that have been used as you used in your previous algorithms, as we used in other things. Same thing has been borrowed to machine learning also. And initialization is the biggest challenge, especially in the Hilbert space. You know, Hilbert space, you might have seen, it's a complex number space where initializing a qubit position to a value which you need is always the biggest challenge. Okay, that is very essential in machine learning because machine learning requires some initialization thing. Okay, even though it works well in simulators, the moment it goes on to your actual quantum computer, it suffers a lot. That's why the accuracy levels are vulnerable now. The accuracy levels are not good on quantum computers because the field is maturing. It is still taking a lot of time. Once people start getting accuracies, you may wonder some algorithms, machine learning problems on quantum classical computers would show an accuracy of 98% and 99%. The moment it goes on to quantum computers, it will show 74%. We had a paper on predicting the cognitive state of human mind using quantum computers. When we ran a program on a classical computer using EEG signals of a human brain state, it was showing 98% accurately it is predicting. But once it goes on to quantum computer, once you make a quantum program on that and we submit to a quantum computer, it was showing 76%, 78%. People are not accepting our paper in good journals because we are not achieving any better accuracy there. It is not because our model is bad, it is because intrinsically the machine has a lot of errors, okay, the noise, because they are dealing with properties like superposition and entanglements. So, of course, memory is the biggest challenge. And the main goal of a quantum machine learning is to speed things up by applying what we know from quantum computing to machine learning. Okay. And of course, as I told you, it is a hybrid model as of now. The quantum data built on hybrid quantum classical models. We still have a classical part as well as a quantum part. Of course, I will not talk about HHL algorithm. You please have a look into this later. This is called Harrow-Hazelden-Lloyd algorithm. This is an algorithm which is used for solving the quantum linear system of equations, which are used for various scientific applications and quantum machine learning models, linear regression, support vector machines, recommender systems. They all depends on this basic HHL algorithm. Okay. You see the runtime complexity. If you have a look into the table given there, it is a quantum linear system problem. We call it as a QLSP problem. So these problems, whatever we call the linear regression, support vector machine, recommender system problems, all are kind of transformed into QLSP problems, and they achieve such a wonderful runtime complexity. See, most of these results are still on a paper in the mathematical sense. Remember, whatever the complexities which you are showing on your screen or whatever is coming up on the paper, still they are theoretical research. If you say something is happening at that level on a quantum computer, many of the research happening, wonderfully people are trying to develop the models. But once it comes to the realism, we are still away from achieving that. Okay. Of course, quantum advantages, I have another 2-3 minutes time with me. One is it definitely improves your training time speed up. Okay. Because you have the QRAMs kind of models have been coming up, quantum random access memory, which will take an advantage of extreme parallelism. It analyzes complex data, okay, because that is the strength of quantum algorithms. Remember, whatever yesterday discussed, all are good at analyzing the data, all are good at looking into the data. Okay, you can definitely create some entanglements, some kind of amplitude modifications, Grovers or Shor's. Shor's is definitely for cryptography. If you look into Grover's algorithm, that is one of the prime algorithm. A lot of people leverage Grover's algorithm for working with large data sets. Okay. Then hyperparameter adjustments. That is one of the advantage the quantum gives for machine learning. Then optimizations. If you look into the all these, whatever the speed ups I've shown, definitely they're all theoretical speed ups. It may not be, people say classical IBM, quantum BM, quantum PCA. You can see sometimes it looks like classical and quantum are all having equal speed. That's why the underlining statement is not in all use cases quantum does well. We have a special use cases where quantum, people are trying to find out what is that use case quantum does well. Okay. Then this is another interesting, maybe I'm almost in the end of my session, quantum tunneling. This is one of the interesting phenomena Here, this is proposed by 1928 by George Gamow. At a quantum level, matter has corpuscular and wave-like property. Tunneling can only be explained by the wave nature. When a particle is incident on a barrier of greater energy, then particle reflection occurs. The particle has the probability of existing within the barrier region, even on the other side of it. That's what is called as tunneling. The people are making use of tunneling, quantum tunneling, for solving many of these optimization problems, especially D-wave. D-wave is one of the quantum computing technology available. They heavily depends on the quantum tunneling and quantum annealing kind of systems, where they make the optimizations. Many of these automotive sectors are making use of D-wave. Okay, I'm not going into details of tunneling. You have QPC, PCA, QSVM. These all the talks will come up a little later. Let me not repeat on that. Quantum CNNs and all. Before I wind up, Indian scenario, many startups are coming up. You can have they are working on simulators, especially now on fluid dynamics, structural dynamics, heat transfer, optimization problems and all. And there are many startups working on QML also, QSVMs, QGANs, QPCAs. You can look into startup space, you will see all these solutions. Communication algorithms, a lot of efforts are happening. Hybrid classical quantum computing models, quantum safe cryptography products are coming up, especially one of the companies in Bangalore called Q New Labs. They are working on quantum cryptography. Quantum annealing, as I mentioned, works are happening. Quantum random number generators, blockchains, critical infrastructure. Especially in academics and research, we are far behind in technology front, and number of researchers working in the national level are few in numbers, in few hundreds. Private sector participation and investment is very minimum. And as Rajesh Pant says, he was the National Cyber Security Advisor to PM. There is no clarity in the quantum roadmap. Okay, so of course DST has a program called Quest, Quantum Information Science and Technology, where a lot of funding they say they'll provide, but still it is you can try out in DST by applying some funding there. Then DRDO has set up a lab in IIT Bombay on quantum technologies, Center for Excellence in QT. I think Dr. Apurva was mentioning about this. And BARC has worked on that. ISRO has worked on for space communication. BARC is also working few experiments on it. An interesting statement by Rajesh Pant. He says in 1993 there was an earthquake in Latur. We created a national disaster management authority which now has presence across the country. Are we waiting for a cyber security earthquake to strike before we get our act together? Quantum computing is going to be the big threat for cybersecurity in future. So the country should get ready for facing the challenges. If they're not ready, if they do not work, start doing a serious research in that line, there will be a disaster waiting. Of course, these are all some use cases I'm not going to talk about. Many companies are working on this space, especially in automotive sector. Automotive is the biggest sector now for quantum computing. So I closed my talk on dot at 11:30. So I gave you some idea of the quantum computing per se, quantum physics part, and some basics, and why quantum computing, and I pushed you into ML part, and I gave you some initial understanding of QML without touching a lot of internal details. Okay, because the next session is on that. So if you have any one or two questions, we can take before we wind up. Sharwani, do you have any questions?
No questions here, sir, on the chat box.
Okay. If there are no questions here and there, since we kept question Q&A throughout, therefore participants might be not having questions. In that case, I'll stop my discussion. Sharwani.
Yes, sir. Sir, there is one question here, sir, from Sangeeta ma'am. Do we have any research direction in privacy preserving in quantum computing?
Privacy is, madam, that's a good question actually. The works which I studied, because I do not claim I studied all the papers or have a look into that. I had a look into that. I looked into mostly in the key distribution side. If you are privacy preserving, you are talking in terms of classical sense, where you talk about anonymization and that kind of stuff. Still you can use classical part for it. Classical is good for privacy preserving. So because privacy preserving is something which is bound to a local machine, okay, or a local server. If someone trying to distribute the private data on a channel to others for making use of it, they can anonymize definitely locally using any classical algorithms, and they can show. I do not seriously find the need of quantum systems there, because any quantum property will help you in preserving privacy, because the whole aim is to see that confidentiality of the communication has been maintained. But anonymization in that context, the question is, we can still rely on classical systems.
Looks like we are done for today's session, sir. Okay, there is one more by Anjali ma'am. Sir, is there any other way we can overcome cyber threat in reality apart from moving to quantum computing?
It's a good question, madam. Actually, cyber security is always a challenging thing. Quantum computing is never be an immediate solution. I had this experience when I was presenting a proposal on cyber security, quantum safe, smart grid communication to one of the panel. They said, why quantum? A simple question they asked, why quantum? See, it all depends upon our demography, seriously. The requirement at the Indian level and the requirement at US level or requirement in other developed country levels are different. The way we progress towards technology and the way others progress towards technology, there is abundant difference. We are good at using technology, someone has produced for it. We are lagging in producing technology. If you are feeling my cyber infrastructure is secured without quantum computing, definitely yes, you are secured. Until unless if the disaster strikes. When the disaster strikes, if someone from the developed country who owns a cyber quantum infrastructure start attacking your cyber infrastructure, you are not there. Till that point, you are safe. Till that point, you are safe. As of now, the complete infrastructure is available only for academic and research. And few automotive sectors are trying out solutions. Because of interest of time, I have not covered any of those things. Automotive sectors are trying out a lot of optimization problems using quantum infrastructure. Till you think you are safe, until unless if that critical infrastructure of quantum goes into the wrong hands and start attacking you, your key systems and your distribution systems, till that point you are safe. Okay. Otherwise, if that happens next year, you are not there. Is that all, Sharwani?
One more question here, sir.
Yeah.
Does quantum classifiers have significant performance for clustering numerical sensor data?
That I think we reserved this question for
Next session.
next session. He speaks specifically on quantum classifiers.
Yes, sir.
Definitely, you can ask him any specific questions on classifications and all. I do not want to get into the other topic now. Okay.
Okay, sir. I think now we can take break and resume at 11:45 for the next session.
Thank you. Thank you, Ganeshan, for joining.
So,
Thank
thank you for delivering a wonderful talk.
you, madam.
Actually, it was very interesting with all the animation and videos. I'm very sure after going through 3 days hectic presentations and sessions from experts, this was actually a refreshing sessions for our attendees here. Thank you once again, Sathish Babu sir, for delivering introduction to quantum machine learning.
Thank you all. Thank you all for the